Hello everyone. Let's analyze. So how nice does a function have to be integrable? Well, to answer that question, we need some way to measure unniceness. Well, what do we mean by this? We know that integration is a bit more forgiving than, for example, differentiation. Differentiability is actually stronger than continuity in the sense that continuity is not enough to guarantee differentiability, but it's more than enough to guarantee integrability. We know, for example, on the real line that if a function is continuous on a closed interval of integration, then the function is integrable. So certainly continuity is sufficient. But we also know it's more than enough. If we have a few discontinuities, no problem. We just break up our integration domain and integrate. So what about multidimensional functions? What kind of conditions have to be satisfied there? So to build up some language of describing how discontinuous a function is and how often, we need a few vocabulary tools in our bag. So suppose f maps a subset of Rn to R, and x naught is in A, and we'll suppose U is a neighborhood of x naught. So we're going to define the maximum change in f over the neighborhood U as delta UF is the maximal difference of f for all two values in my neighborhood. Now, note that if f is continuous at x naught, then one can make the neighborhood U small enough in size so that delta UF is arbitrarily small. Right? That's the definition of continuity. For every epsilon, there is a delta, and if the width of U, in other words, the largest distance across U, is less than delta, then the largest variation of f is less than epsilon. This gives us an avenue for measuring how discontinuous a function is. So we'll define the oscillation of a function f at x naught as, we'll write it omega f comma x naught, as the infimum over all delta UF for every neighborhood U containing x naught. In other words, if I take the maximum variation in every neighborhood of x naught, and then say which neighborhood gives me the smallest variation in f, that's what we call the oscillation. And we'll posit it as a lemma that the oscillation is 0 if and only if f is continuous at x naught. Again, that follows from the fact that we can make the variation or the change in f arbitrarily small if we make the neighborhood arbitrarily small. And since we're considering every possible neighborhood, we can make that variation as small as we like if f is continuous. So just to make sure that we understand the idea, let's consider a function on the real line. F of x is equal to sine of 1 over x for non-zero x and 0 when x is equal to 0. Of course, this should be a familiar function, something that's continuous everywhere except at x equals 0. And for every neighborhood of 0, 1 over x in any neighborhood containing 0 varies over an infinite range of values, meaning that sine of 1 over x varies from -1 to 1 and back to -1 and back to 1, well, infinitely many times. Therefore, the maximum change in f is 2 for every neighborhood of 0. And since it's true for every neighborhood of 0, the oscillation of the function f at 0 is 2. So now we come to our main event. This is the theorem that tells us when a function is integrable. So let A be in Rn. Suppose A is bounded, and F is a mapping from A to R, is bounded as well. And we'll let F tilde be an extension of F to all of Rn in the traditional way we've been extending functions, where F and F tilde agree on the domain A, but F tilde is 0 otherwise. Then F is Riemann integrable over A if and only if the set of discontinuities of F tilde form a set of Lebesgue measure 0. Of course, it's important to point out that F tilde may have discontinuities that F doesn't, specifically at the border. Outside of the closure of A, F tilde is uniformly 0 and therefore continuous. But at the border, if F is not 0 at the border, then F tilde would have a discontinuity at that point. So that's why we have to consider the set of discontinuities of both F and the extension of F. So to prove this fact, let's first address some preliminaries on the shape of the discontinuities. So let D be the set of all discontinuities of F tilde. Well, then, of course, we know that D is all x in the closure of A for which the oscillation of F tilde at x is positive. Because we know that the oscillation is 0 if and only if F is continuous at x. So if it's not continuous, it must be positive. Let epsilon be greater than 0, and we'll let d epsilon be the set of all x in the closure of A for which the oscillation is greater than or equal to epsilon. Of course, if we were to take the union of d epsilon for all epsilon, for all positive epsilon, we would get D. Now I claim for a given epsilon greater than 0, d epsilon is closed. Let's recall the definition of closed. It means that d epsilon contains all of its accumulation points. Well, let's get our hands on an accumulation point. Suppose y is one of them. What does that mean? It means every neighborhood of y contains infinitely many other points of d epsilon. Then the maximum change in F tilde in every neighborhood of y is greater than or equal to epsilon. Again, coming from the fact that d epsilon is defined to be all x where the oscillation is greater than or equal to epsilon. Therefore, if we were to recenter that oscillation at y, the oscillation at y is greater than or equal to epsilon. Because y is an accumulation point, so every neighborhood of y contains values of x that are in d epsilon, so therefore y must also be in d epsilon. Now, that means d epsilon is closed. It's also contained in the set of discontinuities, which is contained in the closure of A, and if A is bounded, so is the closure of A. So since d epsilon is both closed and bounded, we can conclude, thanks to both Hein and Borel, that d epsilon is compact. Okay, so we're going to use the fact that d epsilon is compact to go forward. Now, our theorem is an if and only if statement, so we have to prove both directions. Let's begin with the reverse direction. Suppose that D has Lebesgue measure 0. Okay, our goal now is to show that F tilde must be, or rather F must be integrable. Now, if D has Lebesgue measure 0, D epsilon, which is a subset of D, also has Lebesgue measure 0. Let's remind ourselves what that means. There exists a countable family of open rectangles, Bj for j equals 1 through infinity, covering d epsilon whose collective volume is less than epsilon. Now, since d epsilon is compact, now we already talked about one definition of compactness, closed and bounded, which was a result. The fact that that's an equivalent definition was a result of Heine-Borel. Another definition, or an equivalent definition, is that every open cover permits a finite subcover. And remember, these open rectangles, these B's, are an open cover. So the fact that this open cover permits a finite subcover means that d epsilon is contained in a finite union of these open rectangles. And of course, if I take a finite subset of something whose collective volume is less than epsilon, then the cumulative volume of this finite set of rectangles is still less than epsilon. So let E be a bounding rectangle of A, and let P be a partition of E. Now, we're going to break P into different parts that contain the discontinuities and parts that don't. So let C1 be all subrectangles of my partition that are contained in a rectangle BJ. And remember, the union of BJ for j's 1 through n contains d epsilon. Okay, so we'll call all of those subrectangles that are contained completely in these open rectangles BJ, we'll call those C1. Now, notice that the volume of all subrectangles in C1, because all rectangles in C1 are contained in the open rectangles BJ, which has a cumulative volume less than epsilon, then all the subrectangles of C1 have a cumulative volume less than epsilon. So now let C2 be all subrectangles S of my partition P that do not intersect with d epsilon at all. Remember, d epsilon is the set of all values x where the oscillation of f, which is a measure of discontinuity, is greater than or equal to epsilon. And so we're assuming that C2 is also rectangles of my partition that do not intersect with this set at all. Now, I claim that each subrectangle S in C2 can be repartitioned into subrectangles S prime so that the supremum of F tilde over S prime minus the infimum of S tilde over S tilde of F prime is less than epsilon, right? And that's because my oscillation at all of the values has to be less than or equal to epsilon. In other words, for each x in S, right, in my subrectangle S, which is in the set of subrectangles that do not intersect d epsilon, x is not in d epsilon, implying that the oscillation at x is less than epsilon. So there is a neighborhood u x of x for which the change in F tilde is less than epsilon. If I were to take all the neighborhoods ux that satisfied this equality for every x in S, then I would have a open cover of S. Now, S is a rectangle. It's a closed rectangle, so S is compact. That means since ux is a open cover of x, there's a uxi, in other words, a finite subcover. So I can take a set of values xi for which the neighborhood uxi satisfies this less than epsilon condition. And there's a finite number of them, let's call them m. And S is contained in the union of these uxi's. So we'll refine S in a way so that each subrectangle, S prime, is contained in one of these open neighborhoods UXI. Okay, so the two key facts, the two takeaways from this page of mathematics is that the volume, the cumulative volume of all rectangles in C1 is less than epsilon, and the maximum variation or the maximum change in F tilde in a repartitioning of S in C2 is less than epsilon. So for both my set C1 and C2, I get this less than epsilon property. One in the volume, the other in the change in F tilde. So let's put these two key facts here. Again, coming from the previous page. We'll keep them here. Now, also remember that F is bounded. So there's some K for which the absolute value of f of x is less than or equal to k for all x in my domain. Now, note that my partition P is the union of C1 and C2. Of course, it's possible that C1 and C2 intersect, that there are some rectangles in both, but still, every rectangle in P must be in C1 or C2. So let P prime be the refined partition obtained by applying the refinement to each S in C2. So the refinement we talked about on the previous page. Then the difference of the upper sum minus the lower sum for F tilde over this refined partition P prime is, by definition, right, the difference of the supremum minus the infimum over every subrectangle in P prime. Now, because I can split P prime into two sets of subrectangles C1 and C2, which may have a non-zero intersection, I get a less than equals over my difference of supremum and infimums over my two sets of partitions. Now, already we see the blue team come into play. For all S prime in C2, the difference between the supremum and the infimum we know already is less than epsilon. So that's why we get this fact here. Now, because F is bounded by K, the supremum of F is bounded by K, and of course the infimum is certainly bounded by K, so this term here must be less than or equal to 2k. And now I have precisely the red term up here. So the volume of all subrectangles in C1 is less than or equal to the volume of all open rectangles Bj, which we showed in the previous slide is less than epsilon. So if I factor out my epsilon, I get that the difference of my upper and lower sum is less than or equal to epsilon times a bounded number, right? K is some fixed bounded number, and the volume of E, because E is bounded, is some fixed bounded number. Right? Again, that was part of the hypothesis of the Lebesgue theorem, is that the domain is bounded and F is bounded. That means this term here is bounded. But epsilon is arbitrary. Epsilon is unbounded from below. Epsilon can be made as small as I like. Therefore, F is integrable. So we've shown that if the set of discontinuities has Lebesgue measure 0, then F must be integrable. Now let's prove the forward direction. Suppose F is integrable. Now our goal is to show that D, the set of discontinuities of F, must have Lebesgue measure 0. So again, let's begin with let epsilon be greater than 0. And let us now represent the set of discontinuities as the union of d1 over n for n equals 1 to infinity. Right, of course, d subscript a number is defined as before. Right, d subscript 1 over n is the set of all x where the oscillation of f tilde is greater than or equal to 1 over n. And if I were to do that for every n, for every integer n, then I would actually have every set of discontinuities. Of course, notice the idea behind my thinking. I'm casting D as a union of a countable set of sets. Well then, if I can show that d1 over n has Lebesgue measure 0, and that D is a countable union of sets with Lebesgue measure 0, then I will have accomplished my goal. So integrability of f implies there exists a partition P of my bounding rectangle E for which the difference of the upper and lower sums of my extension f tilde is less than epsilon. Right, so that's the assumption when we say that suppose f is integrable. Right, that's one definition of one way of expressing that idea. So let S1 be the intersection of d1 over n and the boundary of S for every subrectangle in my partition. So I have some partition, so I could think of the boundaries of all my rectangles as kind of a mesh, right? A rectangular mesh. And I'm going to let S1 to be every point on this mesh of rectangles where the oscillation of x is larger than or equal to 1 over n. And then we're going to let S2 essentially be the rest of d1 over n. By the rest, I mean all points in d1 over n that intersect with the interior of some subrectangle in my partition. Right? Because I've partitioned my bounding rectangle, right, d1 over n must pass through, right, some part of my subrectangles, either the boundary or the interior. So d1 over n is equal to the union of S1 and S2. Now, the volume of S1, because it's contained in the boundary of S for all S in my partition, and what is S? Well, S is a rectangle. And the boundary of a rectangle has Lebesgue measure 0, and P is a finite set of rectangles. So the boundary of all my subrectangles cumulatively have Lebesgue measure 0. And S1 is contained in it, so it also has Lebesgue measure 0. Now let C be the set of all subrectangles in P that contain an element of d1 over n's interior. For each subrectangle in C, the difference between the supremum of f tilde and the infimum of f tilde is greater than or equal to 1 over n by the definition of what d1 over n means. Right? It means the oscillation of f tilde is greater than 1 over n. In other words, the maximum difference in f tilde. Of course, the maximum difference has to be the supremum minus the infimum. Therefore, if I were to sum the volume of every subrectangle in C, which remember, C is all the subrectangles in P that contain an element of d1 over n's interior. And I'm going to scale by 1 over n. Now I know 1 over n is less than or equal to this difference. So that gives me this inequality here. Now remember, C is not my entire partition, it's a subset of my partition. So this is less than or equal to if I were to take the sum over the entire partition. But this red term is precisely this red term. They mean the exact same thing. And by assumption, that's less than epsilon. Now, remember, S2 is the intersection of d1 over n with the interior of S. So S2 is contained in the union of all my subrectangles in C. And the volume of all my subrectangles in C is less than or equal to n times epsilon. So we can conclude that S2 is Lebesgue measure 0 as well. Right? Why as well? Well, because we concluded that the volume of S1 is 0, or that S1 has Lebesgue measure 0. So d1 over n is the union of two sets, both of which have Lebesgue measure 0. So d1 over n has Lebesgue measure 0. And now I've got into the heart of my strategy. D is a countable union of Lebesgue measure 0 sets, implying that D is measure 0 as well. And we've proven our results. We've proven the Lebesgue theorem in both directions. So, of course, that buys us quite a bit. We can now characterize precisely what we mean when we say a function is integrable in terms of the continuity or amount of lack of continuity. So let's investigate what this theorem buys us. Let A be a bounded set in Rn. Then A has volume if and only if the boundary of A has Lebesgue measure 0. What do we mean that A has volume? Well, remember, we say A has volume if the characteristic function, chi A, now remember what chi A is just 1 if x is in A and 0 otherwise. Well, we need chi A to be integrable on a bounding rectangle of A. Well, the only points of discontinuity of chi A occur at the boundary, because in the interior of A, chi A is uniformly 1. In the exterior of A, chi A is uniformly 0. So in the interior and exterior, chi A is continuous. But we do have a discontinuity at the boundary, because of course the oscillation there would be 1, because every neighborhood of a point on the boundary contains an interior and exterior point, meaning the difference of f for every neighborhood must be 1. However, if the boundary of A has Lebesgue measure 0, then the set of all discontinuities of chi A has Lebesgue measure 0, meaning that chi A is integrable, which is the exact definition of what it means for a set in Rn to have volume. Another corollary, let A and Rn be bounded, and suppose the volume exist. Then a bounded function of A to R with finite or countably infinite number of points of discontinuity is integrable. Now this corollary is really just a specific instance of the Lebesgue theorem, because a point necessarily has Lebesgue measure 0, and a finite or countably infinite union of sets of Lebesgue measure 0 also has Lebesgue measure 0. So then we have exactly the setting for the Lebesgue theorem. So let A and Rn be bounded and have Lebesgue measure 0. And suppose that f is a bounded function on A. then the integral of f over a is 0. Of course, that's exactly what we would expect to happen for integrating something over a set with 0 volume. Then so long as f is well behaved, that is bounded on a, we should expect that this integral would be 0. So let's prove the statement. Let E be a bounding rectangle of A and P be any partition of E. Since f is bounded, there exists a number k for which f of x in absolute value is less than or equal to k for all x in A. Now, if f tilde is the extension of f to E, then f tilde is less than or equal to k, the maximum value of the absolute value of f, times chi a of x for all x in E. Because f tilde and f agree for x in the domain, and f tilde is 0 outside of the domain. So outside of the domain of A, f tilde is 0, which confirms that f tilde is less than or equal to 0 for x outside of the domain of A. It follows that if I were to take the lower sum of, well, f tilde to be precise, over the partition P, then I would get the sum of all subrectangles of my partition of the infimum of f tilde over this subpartition times the volume of each of these subpartition rectangles. Well, the infimum for each of these rectangles is less than or equal to f tilde of x on the subrectangle, which is less than or equal to k times the infimum of chi of A. Remember, chi of A is either 1 or 0. Well, that has to be 0. Why is that? Well, one of two things happens. Either S is contained in A, which implies that the volume of S has to be less than the volume of A, which is 0, which would imply that S is a trivial rectangle of 0 volume. A trivial rectangle is just one where one of the sides is length 0, having 0 volume. Or S is not contained in A, which means there's some x that's in S but not in A. And if there's an x in S but not in A, well then chi A of x is 0 there. Of course, the infimum of a function that is either 1 or 0 must therefore be 0 for such a subrectangle S. So either way, every term in this sum must be 0, because either the infimum of chi of A is 0 or the volume of my subrectangle is 0. Similarly, the upper sum is negative the lower sum of negative f. And that should be straightforward to see. The supremum of f is negative the infimum of negative f. That should make sense. Now, since the partition is arbitrary, this is true for every partition. In other words, every lower sum is less than or equal to 0, and every upper sum is greater than or equal to 0. So the supremum of all lower sums must be less than or equal to 0, and the infimum of all upper sums must be greater than or equal to 0. But remember that f is integrable by hypothesis. We assumed in our theorem that f is integrable. That means the supremum of all lower sums equals the infimum of all upper sums, which is by definition equal to the integral. And well, the only point where they can possibly agree is 0. And so we've proven our result. Let f map A to R, where A is a subset, a bounded subset in Rn. Suppose it's integrable and that f is non-negative for all x in A. And suppose that the integral of f over A is 0. Then the set of all values for which f is non-zero must have Lebesgue measure 0. So let's prove the statement. Let AM be all values x in the domain for which f is greater than 1 over m. And let's let epsilon be greater than 0. Now, since the integral of f is 0, there exists a partition P of a bounding rectangle E of A, for which the upper sum is less than, well, whatever I want, and right now I want epsilon over m, because I can make the upper sum arbitrarily close to the actual integral. So let S1 through Sk be subrectangles in P that have a non-empty intersection with AM, that is, the set of all values f greater than, or the set of all values x for which f of x is greater than 1 over m. So since f of x is greater than 1 over m for some x in these subrectangles, then the volume of these subrectangles added up has to be less than or equal to m times the supremum of f over these subrectangles. Right? That's because the supremum of f has to be greater than 1 over m. And m times 1 over m is greater than, and m times something greater than 1 over m is greater than 1. And that's how we get this inequality here. So if I factor out this m, then I have the upper sum, or I have something less than the upper sum of f comma p, which is less than epsilon over m. So, of course, the m's cancel and I just get epsilon. Now, my set AM is contained in the union of these subrectangles, right? Because AM, all of AM has to be in some of my subrectangles, and S1 through Sk is all of them. So AM is contained in the union of these subrectangles. But each of them have arbitrarily small volume, therefore AM has Lebesgue measure 0, right? That's the definition of Lebesgue measure 0, right? To be contained in countable sets whose cumulative volume is arbitrarily small. Now, the set of all values x in the domain for which f of x is not 0 is just the union of all AM for m equals 1 through infinity. And a countable union of measure 0 sets, again, has measure 0. So we've proven our result. So let's apply what we've learned to an example. Let's consider the function that maps R2 to R, defined by f of x is equal to x1 squared plus sine of 1 over x2, so long as x2 is not equal to 0, and x1 squared if x2 equals 0. How can we tell that this function is integrable on the open ball centered at 0 with radius 1? Well, we know that the open ball centered at 0 and with radius 1 is bounded. And we also know f is bounded, right? Within the open ball, x1 squared is bounded by 1 above and 0 below, and sine is bounded by negative 1 below and 1 above. Therefore, f must be greater than or equal to negative 1 and less than or equal to 2. So f is bounded and the domain is bounded. Also, we know f is continuous everywhere except when x2 is equal to 0. When x2 is equal to 0, we get a discontinuity. Where is x2 equal to 0? Well, on a line. A line has measure 0, and of course the intersection of a line with the open ball also has measure 0. So, by the Lebesgue theorem, f is integrable. That's all for today.